Hello everyone, welcome again to another lesson from the chapter The Solid State. In this video, we shall discuss about the imperfections or the defects of crystalline solids. As we have learned, in a crystalline solid there is a regular arrangement of the constituent particles. However, this arrangement is generally not found to be perfect. This is because a solid contains a large number of small crystals, and some of these may not have a perfect regular arrangement of the constituent particles. Thus, any departure from perfectly ordered arrangement of constituent particles in a crystal is called an imperfection or defect. Now, there are two main types of defects, which we call as point defects and line defects. Now, when the deviations or the irregularities exist from the ideal arrangement around a point or an atom in a crystalline substance, the defect is called a point defect. However, when the deviation from the ideal arrangement exists in the entire row of lattice points, the defect is called the line defect. Now, when we talk about line defects, there are two main types. We have what are known as edge dislocations and skew dislocations. We shall discuss mainly about point defects. Point defects in a crystal may be classified into the following three types. We have stoichiometric defects, non-stoichiometric defects, and impurity defects. Now, in stoichiometric defects, if the imperfections in the crystal are such that the ratio between the cations and anions remains the same as represented by the molecular formula, which in other words means that the stoichiometry of the solid is not disturbed, the defects are called stoichiometric defects. Now, these stoichiometric defects are further divided into four main types. We have vacancy defect, interstitial defect, Schottky defect, and Frenkel defect. Vacancy defect: when the crystalline substance has lattice sites which are vacant, the crystal is said to have vacancy defect. This generally arises due to the absorption of heat from the surroundings. It results in the decrease in the density of the substance because the mass in the same volume of the crystal decreases. Now, in interstitial defect, when some extra constituent particles are present in the interstitial sites, the crystal is said to have an interstitial defect. This defect results in the increase in the density of the substance because here the mass increases but the volume remains the same. Frenkel defect: if an ion is missing from its lattice site and causes a vacancy or a hole there, and it occupies the interstitial site, the electrical neutrality as well as the stoichiometry of the compound are maintained. Now, this is called Frenkel defect, and this is a combination of vacancy defect and interstitial defect. Since the cations are usually smaller, it is more common to find the cations occupying the interstitial sites. And this defect is also called dislocation defect because the smaller ion, which is usually the cation, is dislocated from its normal site to an interstitial site. Now, this type of defect is present in those compounds which have low coordination number and there is a large difference in the size of the cations and the anions. Now, Frenkel defects are found in silver halides like silver chloride, bromide, silver iodide due to the small size of the silver ion. Since no ions are missing from the crystal as a whole, therefore the density of the solid remains unchanged. Now, in Schottky defect, if in an ionic crystal equal number of cations and anions are missing from their lattice sites so that the electrical neutrality is maintained, this is called Schottky defect. Now, this type of defect is shown by highly ionic compounds which have a high coordination number and has a small difference in the size of the cations and anions. Now, also, as the number of ions decreases as a result of this defect, the mass decreases whereas the volume remains the same. Hence, like in vacancy defect, the density of the solid decreases. Now, let us discuss about non-stoichiometric defects. Now, if as a result of the imperfections in the crystal, the ratio of the cations to the anions becomes different from that indicated by the ideal chemical formula, the defects are called non-stoichiometric defects. Now, these defects result in either excess of the metal ion or excess of the non-metal atoms, and they can occur as anionic vacancies, interstitial vacancies, and cationic vacancies. Now, when we talk about anionic vacancies, here a negative ion may be missing from its lattice site, leaving a hole which is occupied by an electron, which thereby maintains the electrical balance. The sites containing the electrons that are trapped in the anion vacancies are called F centers because they are responsible for imparting color to the crystals. Here, F stands for Farbe, which is a German word for color. Now, for example, when we heat KCl in an atmosphere of potassium vapor, the excess potassium atoms deposit on the surface of the KCl crystal. The chloride ions then diffuse to the surface where they combine with the potassium ions, which become ionized by losing electrons. Now, these electrons diffuse back into the crystal and occupy the vacant sites that are created by the chloride. Now, these electrons absorb some energy of the white light, giving violet color, which is due to the excess of the potassium ions. Now, this defect is similar to Schottky defect, and it is also found in crystals having Schottky defects. Now, when we talk about these interstitial vacancies, the metal excess may also be caused by an extra cation occupying the interstitial site. Here, the electrical neutrality is maintained by an electron present in the other interstitial site. This defect is similar to Frenkel defect, and it is also found in crystals having Frenkel defects. Now, when zinc oxide is heated, it loses oxygen and turns yellow. Now, this is because the excess of Zn2 plus ions that are formed gets trapped into the vacant interstitial sites, and the electrons, they also get trapped in the neighboring interstitial sites. Due to the presence of these electrons, zinc oxide, when heated, acts as a good conductor of electricity. Now, these electrons are excited to higher energy states by absorption of heat. When these electrons fall back to the lower energy states, radiation, which is golden yellow, is emitted. So here we observe golden yellow color on heating zinc oxide. Due to this, it is also known as fool's gold. Cationic vacancies. Now, this defect occurs when the metal shows variable valency, that is, in transition metals. The defect usually occurs due to the missing of a cation from its lattice site and the presence of the cation having higher charge in the adjacent lattice site. Let us talk about impurity defects. Now, these defects arise when foreign atoms are present at the lattice site in place of the host atoms or at the vacant interstitial sites. Addition of impurities changes the properties of the crystal. The process of adding impurities to a crystalline substance so as to change its properties is called doping. Now, this doping can be done for both ionic as well as covalent solids. In case of ionic solids, the impurities are introduced by adding impurity of ions. If the impurity ions are in different valence state from that of the host ions, vacancies are created. For example, if molten sodium chloride containing a little strontium chloride as impurity is allowed to cool in the crystals of sodium chloride form, at some lattice sites, sodium plus ions are substituted by strontium 2 plus ions. For every strontium 2 plus ion thus introduced, 2 Na plus ions are removed to maintain electrical neutrality. Now, in the case of covalent solids such as group 14 elements like silicon or germanium, which have 4 valence electrons, the impurities added may be of elements which may have more than 4 valence electrons, like for example group 15 elements like phosphorus or arsenic, which have 5 valence electrons, or of the elements which have less than 4 valence electrons, for example group 13 elements like boron, aluminum or gallium, which have 3 electrons in their valence shell. The impurities added may be electron rich or electron deficient. The defect thus introduced in the crystals are called electronic defects. Now, suppose we add a small amount of group 15 elements such as arsenic to pure silicon of group 14. Now, it will replace some of the silicon from the lattice site. It has 5 valence electrons and is covalently linked to 4 of the silicon atoms tetrahedrally. The 5th electron thus remains free. This extra electron serves to conduct electricity, and it behaves as a conductor electron just like in metals. This is an example of extrinsic conduction. In this type of conduction, current is carried by the excess electrons in the normal way. This is called N-type semiconduction. N stands for negative charge. Now, when group 14 elements like silicon are doped with group 13 elements like aluminum, the silicon atoms at some lattice sites are substituted by those of aluminum. Now, as group 13 elements have only 3 valence electrons, they can form 3 covalent bonds with the neighboring silicon atoms. Thus, a hole is created at the site where the 4th electron is missing. This is called electron hole. An electron from the neighboring atom can jump to fill up this electron hole, but then an electron hole is created at the site from where the electron has jumped. As it continues, the electron holes will move in a direction opposite to the direction of flow of electrons. Now, when an electric field is applied, the electrons move towards the positively charged plate and the electron holes move towards the negatively charged plate as if they carry a positive charge. Hence, silicon and germanium doped with electron deficient impurities are called p-type semiconductors.